to Studio 68. This is the AGR Breaks It Down podcast. Once again, I am Dominic Baker, your host, and with me today is Gary Smay, one of our senior scientists, semi-retired. How you doing, Gary?
I'm doing fine. It's a pleasure to be with you today. I've been here for 52 years, working at AGR, and it's a pleasure to be in Studio 68 to talk about vertical load.
Vertical load, yeah, that's exactly what we're going to be talking about today. Now, this was a subject that came up with our kind of parent, AGR International. We had a discussion on some vertical load testing, and it developed a question that we'd kind of want to review and maybe expand upon, talk more about vertical load as a whole. So I guess let's just start with the context, right? What kind of vertical loads apply to a container, generally speaking? What do we generally see in the industry? All that, just provide some background.
It's an interesting topic because it's not a very common load that's discussed a lot. However, it's an important load because all containers have to have a closure. Mm-hmm. And the closure has to be sealed properly on top of the container, especially for carbonated products. So if you have a bottle that has a crown finish on it, the force that's required to seal that closure might be on the order of 800, possibly as high as 1,000 pounds. That's not commonly known throughout the community.
Yeah. Mm-hmm.
And I think people are oftentimes amazed that bottles can endure and withstand that kind of load or that kind of force on the top of the bottle. Now, other types of closures, such as roll-on pilfer-proof closures or plastic screw-on closures, you don't need quite as much load or force to seal those closures properly. Mm-hmm. So there, the capping force might be 200, maybe as high as 400 pounds. And sometimes you have simple closures that only require a few hundred pounds to properly apply the closure and to seal it. Mm-hmm. So the forces in the capping operation are the major ones that we have to be concerned about.
Right, and we actually have a little graphic up here behind us that basically restates what you had just said. There's several different styles of containers. A lot of times if we have a pressurized wear, we're going to need a little bit more capping force to maintain a proper seal at that sealing surface, right? So upwards of about 1,000 pounds or 450 kilogram force, right? If it's non-pressurized, we can deal with a little bit lower. Down to about, what, 200 pounds?
200 probably is the
acceptable.
lowest, yeah.
Yeah. But then we have another case of
Yes.
vertical load, right?
And this is the one that's probably less well known. And that's the forces that a bottle has to endure as they're sitting in a warehouse. Mm-hmm. After the bottle's been filled, capped, labeled, packaged in the appropriate system, mm-hmm. they're then placed on pallets. Mm-hmm. And now these pallets are put out into a warehouse for storage until they are transported to be sold. Yeah. So you'd have one pallet, and maybe you might place 2 or 3 other pallets on top of that one. Now, if these pallets are stacked appropriately, mm-hmm. The forces that are imposed on the bottom row of the bottom pallet aren't necessarily all that high. They're well distributed over a few hundred bottles. So the force on each bottle, pretty minimal. The problem occurs, however, if the stacking of these pallets is not correct. And if they get skewed off a vertical a little bit, now all of that force, all of that weight of the filled bottles in the pallet might be imposed on the bottom row of these bottles on the bottom pallet. Mm-hmm. And now, because of the skewing of the pallet distribution, those bottom bottles might experience a few hundred pounds of load on each of them.
So the pallet kind of skews maybe off to a corner, and that one corner is bearing all the weight of the giant tower of containers that are filled, and you start getting a couple 100 pounds. We have up here just a general number of about 400 pounds. So, and really all that number is to say is in comparison to some capping loads, you might not be as concerned.
That's generally correct.
Yeah.
What we've listed on the table here is what we would expect to be the maximum loads. So 400 pounds in an uneven stacking configuration, that's probably the maximum. More typical, a few hundred. But still, we have to be concerned about that.
Right. Add a factor of safety to
yes.
it in a way.
Because various designs of bottles, some of them are able to withstand enormous amounts of vertical force, and others not so much.
Yeah. And we'll actually get into that discussion a little bit later. But first, why don't we talk about testing? Like when we do quality control and we're testing for a vertical load strength, how do we go about doing that? Well, we have a machine, right?
Yes.
Dedicated to that purpose.
Yeah, there's a vertical load tester. It's used in conjunction with our ramp pressure testers, whichever model you might happen to have. So the pressure generated by the pressure tester is used to drive a piston, which actually applies the load onto the top of the bottle in our vertical load tester. And the general rule of thumb is that if you take the readout of the ramp pressure tester, if it's in units of PSI, you multiply that by a factor of 10, and that's the actual force in pounds that's being generated or put on the top of the bottle that you're testing. Now, if you're using a metric system, the output of a metric pressure tester is multiplied by 50, and that gives the load that's applied on top of the bottle in kilograms.
Right. Okay. So we got, the two different systems. You get your imperial, you got your metric, but the basic principle of it's attached to a ramp pressure tester. We use that as kind of the driving force for our piston, right?
Yes.
And that crushes down onto the top part of the bottle. And I believe there's a limit to the amount of force we can put in a bottle, right?
Yes. Generally, the upper limit is 5,900 pounds, which off of the PSI pressure tester is a pressure level of 590. Now, some of our pressure testers, ramp testers, will go to a maximum of 890 PSI of pressure. We don't allow that to occur onto a bottle. Right. Obviously, you'd be dealing with a vertical load tester of almost 10,000 pounds, and you just don't want to do that.
So 5,900 pounds, we're talking like, 3 tons?
Yes.
That's a lot of weight bearing down on a bottle.
It's kind of amazing when you think about a bottle such as this one. It's a amber 12-ounce long neck beer bottle, non-refillable. So it's relatively light in weight. This one bottle can withstand easily a load of 5,900 pounds. So when you think about that in the context of weight, you could probably put a medium-sized SUV on top of this one bottle, and it would survive and not break.
No kidding. No kidding.
It's pretty amazing. In fact, I've seen pictures in the web where a city fire truck, these mammoth big fire trucks, I'm sure they weigh 10 or 15,000 pounds, were perched on top of 4 bottles like these, one at each tire.
So it almost makes you wonder why we're having failures at the capper and things like that, right?
Well, there's 2 factors that can be involved in failure at a capper. The first one, and probably the most predominant one, is the design of the bottle.
Right, of course.
The second one, and it's the one that we really need to talk about, is the surface condition of the glass.
Okay.
So let's talk about design first.
Sure.
This particular bottle is a very good design for vertical load. This is the amber 12-ounce long neck beer bottle. It's very much a straight cylinder shape.
Very standard for most beer containers, yeah.
And the best shape for vertical load is, in fact, a straight vertical cylinder. So this particular bottle easily could handle a fire truck.
Okay.
We have another bottle, which is a 12-ounce amber Michelob bottle. And the design we're looking at here was one of the first designs that were ever tried for Michelob. You can see that this one deviates significantly from a vertical cylinder.
Yeah. It almost looks like a lava lamp in my eyes.
Well, to you maybe. To me, it looks like a champagne glass or something like that.
A little fancier.
Yes. And this was the intent of Anheuser-Busch at that time. They wanted to create a design that was unique, that was easily recognizable for the consumer when they walked into a store. They wouldn't see the standard old beer bottle. They saw something that was unique and
iconic.
Attractive.
Yeah,
yes.
Exactly. Something that just immediately stands out on that shelf. You go, that's what I want. You're not looking at any other bottles because this is what catches your eye.
Yes.
Yeah.
And so from a marketing point of view, perfect.
Perfect. Yeah. That's what we
From
want.
a technical point of view, not so good.
Your engineers are going to be a little upset with this one.
This one deviates obviously from a straight cylinder.
Mm-hmm.
The bulbed sidewall,
Mm-hmm.
and then the constricted waist, and then a very dramatic bottom shape are very bad for vertical load.
Right.
What this means is, as you apply a certain force on the top of the bottle, because of the complex shape, you're going to be generating a fairly high amount of stress.
Mm-hmm.
And it's the magnitude of the tensile stress that dictates whether glass fails or not.
Right.
If the stress exceeds the strength of the glass, you have failure.
Well, that sounds like something we teach in one of our Fracture 1 courses, right? That's
Yes.
the fracture equation.
And this particular bottle was, I think, the second generation of the Michelob shape,
Mm-hmm.
and it did not perform well in a capping operation. And so they had to modify this even further by raising the heel contact point
Mm-hmm.
and rounding out this very, very pronounced heel shape,
Yeah, it's quite pinched.
very pinched, into something more rounded.
Okay.
And that's the shape that you normally associate with the old style of Michelob bottles in the past.
Okay. Well, that's very interesting. So that has a lot to do with the design side of things. And you mentioned there was a second thing, which was included in that fracture equation you had just brought up, which was that glass surface strength, right?
Yes.
So I'm going to bring it back here. We still have up on the side this vertical load tester. So when we break this bottle, we have, I believe it's called a cullet can, right? That's going to catch the
Yes.
cullet in there. The reason I'm bringing this up is because that could actually affect your testing down the line if we're not cleaning that cullet out, right?
Yes. The purpose of the cullet can is to retain the fragments of glass in case a sample breaks. You don't want those shards of glass flying all over the place. So the cullet can is designed to contain that.
Mm-hmm.
However, once you have a broken bottle and you have shards of glass, you need to be very careful to clean that cullet can, or in the case of the picture that's shown here, that bottom platen, you want to make sure that the cullet is taken away from that, so that when you put the next bottle in the tester,
Mm-hmm.
you're placing it on a nice, clean, solid surface, and you're not placing it on a bunch of cullet that's lying there, because
Mm-hmm.
as the load is imposed on the top of the bottle, that's going to push the bottle down into those pieces of cullet. That's going to create damage on the bottom of the bottle, and that could, in fact, influence your test results.
Right.
And so you want to test the integrity of the bottle and its surface condition. You don't want to test an artifact of the test of having cullet lying around all over the place.
Of course. So we want to make sure it's a good, accurate test.
Yes.
And as we know, glass, as you scratch the surface or do any kind of surface discontinuity or flaw, it's reducing that strength down. So if we want an accurate test, got to make sure that's clean. And
Yes.
I believe here at AGR, one of the methods that we use actually is we tape the bottles. We completely wrap them in tape so that when we do crush them down, and we have an image that we'll show later of a fracture pattern that
Mhm.
is distinctive to vertical load, we're able to maintain that fracture pattern because of the tape. And that also reduces the amount of cullet that gets
Yes.
thrown around in the vertical load tester. But that helps us further identify, again, the fracture pattern, where that origin might be, and help us with that fracture diagnosis.
Yes.
So two different ways to kind of handle the cullet a little bit and continue testing in a more pristine environment.
Yes. Now, we do need to come back to the surface condition.
Mm-hmm.
Once again, if you're testing bottles as they're produced, selecting them off the end of the leer, ideally, those glass surfaces have never been in contact with another bottle. They may have been in contact with certain devices in the manufacturing of the bottle to move them around in what's called the hot end. But typically, those contact materials are designed so as not to create damage on the glass surface. So when you choose a bottle to test from the end of the leer, that glass surface is going to be what we call pristine, fairly well not damaged or pretty clean,
Mm-hmm.
and it's going to exhibit extremely high strengths. So if you test a bottle off the end of the leer, you may not be able to break it in a vertical load tester. And so the value of the data you derive is very questionable, because if you can't break the bottle, does that mean the bottle's not going to break in the capper? Well, you have to be worried about the damage that might be created on that surface from the time it leaves the layer until it gets to the capper.
Right. So let's think about that, because you mentioned they're in the manufacturing environment. They have specialized equipment, so as not to kind of scuff the bottles, right? We're trying as best as possible. So as they leave our plant, the manufacturing plant, the glass bottles are still in that pristine condition.
Yes.
They're going to be transported likely on a truck, bulk palleting. It's going to get to that filling line. We're going to put it on that line, and we're going to have it bang into other glass bottles until we get to the capper. So at some point, as you mentioned, we're going to pick up some sort of handling damage, some frictive damage, some scuffing, and that's going to lower the strength of the glass.
Yes.
And that's where we're concerned is we had the two conditions, right? The capper and then storage at the warehouse.
Yes.
Typically more so when it's filled than at a manufacturing plant when they're all empty, right? Because the weight's not so big. So that's what you're trying to get at, right? Is when we test this vertical load condition, we should be simulating, right, damage.
Yes. You want to perform a test to give you an idea of how well that bottle, as it's designed, and then as it's manufactured according to the blueprint specs, how that bottle is going to perform when you then apply the load predominantly at the capper, because that's going to be the much higher force.
Right. So we have a piece of equipment here that we designed at AGR called the line simulator. You want to explain to me how this works?
The line simulator is designed to create a testing environment that will create a reproducible amount of damage on the glass surface. So you can take a set of containers and put it into the line simulator, run it under certain parameters, and that will create bottle-to-bottle sliding contact, creating what we call frictive damage on the glass surface. And if you test one set of bottles to another set with exactly the same conditions, you want to make sure that those resulting strengths are the same.
Of course.
So the line simulator has been developed over a number of years to create that reproducibility that you're looking for. And this is one of the ways in which you can take the relatively pristine bottles off the end of the layer, subject them to some abuse, some line simulation that will reduce the surface strength to the level that you would expect that bottle to exhibit when it goes into that capping operation.
Okay.
And now when you test those bottles for vertical load, you're going to get an accurate, real-term, real-life idea. Is that bottle going to survive as we expect it to?
Right, because you're not going to cap a pristine bottle. It's going to go through, like we said, that transition from the manufacturing plant to the filling line, kind of banging around in the truck, kind of banging around the filling line. Actually, that's one of my primary jobs here at AGR is I go to these filling lines, and they can be oftentimes quite messy with the number of times that the bottles are rubbing together. Maybe they have high line pressure. Maybe it's just some glancing impacts. Sometimes they're handled abusively, sometimes they're handled pretty well. But the idea with this line simulator, right, as you were saying, is just to get a reproducible, very typical level of damage, such that when we do our testing for the vertical load, it is in the same real-world application as what we would see at a capper.
Exactly, and that's the whole purpose of the test.
And so let me ask you this. Is there any other ways to simulate damage that would be just as appropriate as maybe line simming?
Over the years here at AGR, we've done extensive testing on the strength of glass as it relates to various surface conditions. And one of the other ways that you can simulate surface strength is to take a pristine bottle off the end of the leer and then hand abrade it with emery paper. And for a non-refillable bottle, if you use 600 grit emery paper, you will reduce the surface strength of that glass to the minimum expected level that we would expect a non-refillable bottle to exhibit throughout its entire lifetime. So that's another way that you can reduce the strength so that your vertical load testing now has meaning and you can be predictive of it.
Sure. So as a follow-up question, the damage, though, right, the type of flaw that I'm creating on the line simulator versus, say, the emery paper, it's going to be different.
Oh, yes, quite different.
Is that going to affect my testing at all?
No. Keep in mind that the whole purpose of treating these pristine bottles is to affect the surface strength. Now, in real world, we expect bottle-to-bottle sliding contact to create frictive damage,
Right.
crescent cracks.
Right.
The use of the line simulator will mimic that. It will create bottle-to-bottle sliding contact,
Same
resulting
damage
in frictive damage, crescent cracks.
Yeah.
The use of emery paper, however, creates what we call cleavage scratches. They are different. However, what we are primarily interested in is the strength value. We're not really too concerned about how we get to that strength value. We just want to reproducibly create the strength that will enable us then to predict the performance of these bottles in the capper.
So as long as the frictive damage and the cleavage damage both bring that strength level to roughly the same region you would expect, I don't know, maybe we're reducing it down to 10,000 psi, something in that ballpark, right?
Yes.
That's all we care about, because that's the reproducible test of the strength at failure, right, in the capper.
Yes, and again, that's the whole purpose of doing vertical load testing.
Okay.
Now we can get to another comment about vertical load testing later when we look at stress distributions, and we'll just reserve that discussion for then.
Sure. I have another slide that actually kind of gets a little bit deeper into this discussion of line simulation. So what we have here is a kind of data point projection of 25 samples, I believe, that were tested for vertical load. And we did this in the metric kilogram force. And we have a mean or an average force of 10,045 kilogram force. Thousand, excuse me. I'm sorry, I don't know what I said there. And there's a projection, so we're able to project a lower end strength of a larger population, assuming that this is representative of about 400 kilogram force.
Yes. Now, with that projection, that's probably a mean minus 3 sigma value.
Yes.
So you're looking at a tail end of the distribution where you're dealing with a fairly small portion or percentage of the total population. It's still at that force level, you're right on the borderline of whether that bottle is going to survive a real capping force or not. And so from this particular distribution, you would have to conclude that this bottle may need to have some attention paid to it to improve that vertical load strength a little bit.
Right.
By maybe 20 or 30%, either through small design modifications or possibly through a little bit extra weight on the bottle to increase the glass thickness in the sensitive regions.
Okay. Now, I did mention this particular data set was from a line simulated sample set. How would this look different if we did it off the Lear?
The off-Lear strength, you may not have even been able to break this bottle. The mean was around 1,000 kilograms. You would easily triple that value.
Wow.
With this bottle off the end of the Lear with no damage on the surface at all. And in fact, when you do a lot of vertical load testing off the Lear, of samples off the Lear, many times you can't break them. And so instead of seeing this nice distribution, it'll be truncated at the upper level.
Yeah, and the mean, the average, all that standard deviation is probably higher than what's reported because you can't even break the bottles regardless. So, and that data wouldn't be useful, again, for the use case scenarios of the capper and the storage at our filler.
Yeah, all it's going to tell you is you have a well-built bottle as you manufactured it. That's all you can tell, and has no bearing on the performance in the capper at all.
Okay. So what we're trying to get at here is performance testing, right? We're trying to simulate the real environment in which these bottles are going to undergo the loads of vertical load in this particular case, and whether or not they're going to hold up to those standards.
That's right.
If we test the pristine bottle, like you said before, we could put a fire truck on some of these cylindrical beer bottles if we're designing them for vertical load. But as soon as we start putting damage on them, that fracture equation comes in, and then, I don't know, based on some of projections, you could be breaking, maybe 1 in 1,000 or so bottles at the cap.
And that kind of breakage level is not acceptable.
Right. So that's what we're trying to get across. That's what we're trying to tell you guys is, hey, when it comes to vertical load testing, make sure that we're doing some sort of simulation, whether that's the emery
Yes.
paper or the line simulator, just, getting ahead of that issue at the capper.
That's exactly right.
Okay. So let's jump into this design part of it, because we did talk about the straight wall container. We talked about the Michelob bottle. We have a couple other examples here, and they're quite fascinating in my opinion.
This is a small capacity beverage container of some sort. I'm not exactly sure what the product was in it. It's made of flint glass. It has a straight cylindrical sidewall, but on the top, above a very pinched shoulder, is a bulbous neck region, simulative of a snowball.
Yeah, it looks exactly like one, yeah.
And this was termed a snowball bottle. The finish is typical of a vacuum-packed ware, and so there's no need here to apply a great deal of force to seal, from a carbonation point of view, pressure inside the bottle.
So we're talking a couple 100 pounds, if that.
The load's not going to be very high. However, this is not a very good shape for vertical load. The rapid constriction right above the shoulder contact into this constricted neck region is going to generate a fairly large amount of vertical load stress for the load that's applied. And then up here in the bulb, which simulates a snowball, it's quite pretty. And again, from a marketing point of view, this is perfect.
Yeah, that's attention grabbing.
Yeah. And you'll want to drink that, whatever it is. However, up here in the bulb, we have a lot of embossing. And sometimes when you create embossed features like this, you are prone to checking it during the manufacturing process. With this somewhat non-cylindrical portion up here in the neck, you have checks in there, even though you're applying only a marginal amount of vertical force.
Right.
The vertical load stresses here in this bulbous region could be high enough to break a bottle that has checks in it. And the shoulder contact is going to see even higher stresses.
Okay.
And so I'm not saying this is a poor design. It's not. You just have to be careful during the manufacturing that you are not creating a reduction in the glass surface strength that could result in problems later on in the filling process.
Right. Now, you mentioned, we did this kind of like embossed feature where that snowball is. Now, if we had done maybe a slightly different process to achieve the same desired effect of, the snowball look, whether they had done some sort of targeted frosting, if that's even possible, or maybe they chose a less complex embossing feature, we would reduce the number of checks and potentially eliminate part of that problem. But with the way they had done the first design, it could be a little worrisome.
This is not a poor design.
Right.
It's a unique design.
Very.
But because it's unique and has some features that could be compromising for vertical load performance, you just simply have to be careful how you make it.
Okay. Now we have some other fun bottles here. This is a cosmetic guy. It's like a gray, almost like a purple in a sense. But why don't you go ahead and tell me a little bit about this guy?
When you take a look at this shape, we have a very flat shoulder, straight sidewalls, and then a finish located in the middle of the top.
Yep.
Very typical of cosmetics. However, this shape for vertical load is atrocious. When you place a load here on the top, you're going to create huge amounts of bending around the junction of this flat shoulder with the sidewall. Now, this can be tolerated because in cosmetic industry, the vertical force to seal this is hardly anything at all.
Right.
Because you're more concerned about crimping something than you are pushing a seal down on the top of the container. So, even though this shape from a pure vertical load technical viewpoint is bad or poor, it's highly tolerable because the forces aren't very high.
So designing for your specific product necessarily.
Yeah. And again, this is typical of cosmetics and very serviceable. Nothing wrong with this design because it was tolerant of low forces.
But if we tried to put a carbonated beverage in that, say we grew it up and made it a 12-ounce container, same design, then you'd start seeing some problems, right?
Well, vertical load might be the least of the problems.
Well, that's fair. That's fair. Yeah, we got some corners on that, and pressure doesn't like that. But
No.
From a pure vertical load standpoint, as you were saying,
It would be a problem.
it would be a problem. So kind of keeping that all in mind when we go through some of our iterative designs of our glass containers and the conditions they're going to be put under, right? As we've talked about before with the testing, we need to make sure that we're testing for the same conditions in terms of simulating that damage. We also need to understand are we capping something pressurized? Does it need to be that 1,000-pound capping force? Or are we working with something like the snow ball bottle, right, where the capping forces will be much lower?
Right.
We can get away with more
right.
design, I don't want to say flaws necessarily, but
Design features
design features, yeah. That's a
that
good way
make
of
the
putting
bottle
it.
unique.
Exactly. So depending on that use case scenario, you can kind of get away with some extra things. But
Yes.
We have one final slide here, and this actually has this fractured image of the bottle over here on the right. Now, really what's happening is there are cracks at the shoulder, and as you see on the animation here, there are bands of tension stress.
Yes.
So this is a finite element analysis that we've done in a computer-aided design. I think this was SolidWorks. Where we have the container showing the stress of a vertical load. And it's very localized, right, Gary? It's
Yes.
just in the shoulder and the heel
The
mostly.
stresses on the outside surface, the ones we're concerned about are the regions that will exhibit a tensile stress. Because once again, glass only breaks under the influence of tension. So for vertical load, we have to be concerned about where are those tension stresses being generated and what are their magnitudes. And as shown here in this depiction, we have two bands, shoulder contact point and heel contact point. And for vertical load, this is the areas we have to be concerned about. And this is why if you have a fairly cylindrical bottle like is shown here, these stresses are reasonable.
Manageable.
Yes,
Yeah.
very manageable. If we were to do that simulation with this old Michelob bottle,
With the pinched heel.
the
yeah.
stress magnitudes would be significantly different. Now, this also points out that if we want to evaluate the bottles that we are producing for quality, we typically will subject the bottles to either thermal shock or internal pressure because those two loads create essentially a global tensile stress across the whole outside surface. If we tried to use vertical load as a quality test, if we were creating flaws in a shoulder-heel contact, that would be a good test. If we had flaws in the sidewall, in the bearing surface, in the bottom somewhere, this test would never find them.
So what you're saying is for those glass manufacturers, they're looking specifically for flaws in their manufacturing process. So if they have some sort of check or stuck glass or there's some sort of issue with the bearing surface, pressure and thermal shock are likely going to find those manufacturing flaws. And we can toss those bottles before we send them on to whatever filler is going to be filling that container. With vertical load, however, if I have a check in the bearing surface, am I going to find it? Never going to find it.
Probably not.
And that's because we don't have tension stress there. It's
right.
just in the, well, it depends, I guess, the design of the container. But
It does.
For a standard like beer bottle like we have up here,
Right.
The shoulder and the heel contact,
So
generally speaking.
what this brings out is, once again, that vertical load is not a good test to evaluate the quality of the as-built container, as-produced container.
Right.
However, it still has value because you still want to be able to predict and understand, is this bottle, the design, its weight and its thickness going to survive the capping operation?
Right.
And so there, we abrade the glass surface, subject it to vertical load testing,
I see.
and you get valuable data.
So in this case, what you're kind of leading at is we have, you can test it off the layers is vertical load, but we're not, there's better tests, right?
Yes.
We have that pressure, that thermal shock to find those flaws. So even if we consider it from a quality control test, we got better things to do. In terms of testing it for a design and making sure it's acceptable based on operating conditions, we got a pressurized container, it's a long neck beer bottle, whatever the case may be, we should still be abrading it off the leer or simulating the damage in one way or the other to test.
Ideally, yes.
Ideally.
Because once again, you want to make sure that your bottle has been designed and manufactured to meet the minimum strength
Mm-hmm.
and still perform and handle the loads that are going to be applied to it. So yes, in that regard, if you're doing predictive work,
Mm-hmm.
proof of design work, yes, abrasions are important. However, keep in mind
Mm-hmm.
that thermal shock and internal pressure are also used to try to detect the presence of manufacturing flaws or
Mm-hmm.
flaws that are created during the manufacturing operation that could compromise the performance later on. And so there, you will test bottles off the leer
Mm-hmm.
in their pristine condition because now you're looking for,
Specifically those flaws. Yeah.
So there's two types of testing.
Mhm.
Predictive testing to make sure the bottle will perform to its intended purpose,
Mm-hmm.
and quality testing to assure that
I
the
see.
glass bottles they don't have an unexpected flaw on the surface that
Right.
you don't want to pack.
Two entirely different goals.
Yes.
Okay, two entirely different tests for two entirely different goals. That makes perfect sense. Wow, Gary, that's a pretty good time, I think, to wrap it up, our discussion on vertical load. We were able to talk about the testing, about design, about all the different stresses, some of the FEA plots. One final thing to mention: how do I look at this bottle and kind of know immediately, this fractured bottle that I have over here, that's vertical load?
Well, it's a very unique pattern, and all fractures have unique patterns. For example, the fracture pattern due to an impact breakage
Mhm.
is different than if you compare it to a bottle that broke from thermal shock. Those patterns are quite different if you compare it to a bottle broke from internal pressure.
Mm-hmm.
And here we have shown the pattern for vertical load, and it is unique again compared to the other three. Typically, in this particular case, we're dealing with a fracture in the shoulder contact region.
Mm-hmm.
It consists of a short vertical split with looping cracks around to either side.
So it's
very characteristic.
localized to that
Very-
shoulder region.
Very
right?
much confined to that
Mhm.
shoulder contact region. A breakage in the heel contact is going to be similar
Mhm.
in its appearance. And this particular pattern is very unique to vertical load. If you have a bottle that's taped
Mhm.
and you subject it to some unknown load, let's say it's a quiz,
Sure.
and your boss comes to you and asks you, how did this break?
Mm-hmm.
This particular pattern, you can impress him by saying this is a vertical load
Vertical
failure.
load. No. And that's because we know what the stress patterns look like.
Yes,
And we know that glass fills under tension stress.
yes.
And because of that, these cracks are going to turn away from those regions of compression because we are compressing the bottle, right? In
Yeah, the
vertical load.
sidewalks are going to be exhibiting compressive stresses initially. And so any crack that forms in the sidewall can start to propagate upwards and downwards, but as soon as it encounters those compression levels, it has to turn away
Right.
because it can't go into compression.
It's going to look back for those fields
Yeah.
of tension stress. So
And that's why you get the looping crack.
that's why we get the looping crack. So we're able to identify, based on our knowledge of the stresses, to get us to that fracture pattern, to get us to, that's a fracture pattern that reminds us of a vertical load break. And we're able to diagnose from there. And that's a lot of what we do here at AGR. We do a lot of fracture diagnosis. So if you're struggling on your own to identify some of these issues, go ahead and contact us and we can help you out with identifying, said failures. So that's all we have for today for this episode. Gary, thank you so much for joining
You're
me.
very welcome.
It's been a pleasure.
It's always interesting to talk about how bottles break.
Absolutely. Hopefully we'll have you on again in a future episode. For the time being, thank you all for joining us, and we'll catch you in the next episode.